Okay, so I need to finish up a little bit of stuff about the immune system. Had I gotten to talking about antibodies?
Yeah.
How far through antibodies did I get talking? Okay. I got into this. Did I explain all 5 parts? Okay.
Yeah.
Did I get to the types of antibodies?
No.
Okay. So, so far as I've been talking about antibodies, each lymphocyte, when it's produced originally in the red bone marrow, makes a unique antibody that'll recognize just one particular antigen. Once they're activated, a B cell proliferates to give rise to the active B cells that become plasma cells and the memory B cells. All of those cells are clones of the first activated copy of it. And so all of those B cells, plasma cells, make antibodies against the same antigen. But a given plasma cell will make 5 different types of antibodies based on how they interact together, I suppose you could say. Actually, I'm going to get out of the presentation. I'd rather go to rather go to the books. Come on. Representation of this. So let me just back up to that part. Okay. So the reason I went here, the one in the presentation I've been using for this from another book, I like this because it shows some of the some data that has to do with each of these types. These are all referred to as Igg something as an abbreviation. They are immunoglobulins, which is just another word for antibody. And so capital I, lowercase g is just an abbreviation for immunoglobulin. And then they have M, G, A, E, or D, which really corresponds to a Greek letter that's the designation for the particular heavy chain, gene. Configuration, I think that's what I mean. Because what makes these different is how they interact with each other, which is taking place where the heavy chains have their constant regions. Now, instead of just going across the table as it's laid out here, I'd rather go in an order that has to do with how prevalent the antibody is in your system, which is basically this column that says percentage of total antibody in serum. So the most common type of antibody, according to this table, is the IgG. It's found primarily as a monomer, a single antibody in the kind of Y shape that we usually picture antibodies, meaning that it doesn't pair up or make larger assemblages with other antibodies. So usually when we think of antibodies, this is what we're thinking about. It's found all over the body. A very important role that the IgG plays is that it crosses the placental barrier, which means a mother will share her immunity with the fetus that's gestating so that it has its ability, it has a passive version of an adaptive immune system when it's born, because its adaptive immunity won't be ready to go for 6 months to a couple of years. So it gets those most of the antibodies from its mother through the placental transfer, which is IgGs. The next most common type of antibody, 13% according to this table, is the IgA. It's most normally found as a dimer, which means that 2 antibodies are linked together. And so they're, the heavy chains link up with the antigen binding site sticking off, sort of two on either end there. The IgAs are often found in secretions, so they have an additional protein associated with them called the secretory component, which is sort of a fibrous protein that wraps around it. I actually don't know that much about the secretory component. It might just stabilize the dimer configuration for the various secretions that we find it in. Finding it in secretions, down at the bottom it says it's found in mucus, so all mucous membranes are going to contain IgAs, helping to counteract the ability of pathogens to cross those mucous membranes. Tears and saliva, well, saliva is kind of the mucus of your oral cavity, so to speak. So it's going to contain that, just like the rest of the mucosal lining of your digestive tract. Tears are secreted over the surface of your eye, and so any pathogens that get onto the surface of your eye, which doesn't obviously have skin covering it, it's going to have these to help protect it. And then the last thing it says there is colostrum, which is the initial milk that's produced by the mammary glands. So most of the immunity that a newborn has comes from IgGs that it got in utero across the placenta. But after the baby's born, it still doesn't have a functional adaptive immune system. So it needs to get some immunity, which it gets through the milk from the mother, and that's going to be IgAs. Now, the issue of whether to breastfeed or not is a little bit contentious, and I don't want to get into that. Some people choose not to breastfeed, some people do. One of the things that proponents of breastfeeding, proponents will make a point of is the immunity of it. I'm not positive how big a part of the passive immunity the newborn has actually comes through the colostrum. And when I said initial breast milk, that means at the beginning of a feeding, the first bit of milk that the baby gets is called colostrum. And early on, before the mammary glands are really producing much milk, that's pretty much all that's present in the first, couple or few feedings. It's not just antibodies and colostrum. It has lactose and proteins and that sort of thing too. It has a lot of that in it. Anyways, I was starting to say, I'm not sure how important that is for the passive immunity for a newborn. It would seem that anything that the mother's immune to, the baby is going to be immune to thanks to the IgG transfer in utero. But if she's exposed to something new, then possibly if she develops an antibody or an immunity to something after she's given birth to the newborn, that can be passed through IgAs. Of course, as I've been teaching this for years, all of this was kind of theoretical, but I now have a little experience that actually bears right on that particularly, which is my wife, I think the week right after spring break, I don't know, some week, I can't remember exactly when it was now, got sick, fortunately not horribly sick. She just needed a lot of time to rest. And so one day, actually, yeah, I must have canceled class on you guys one day, didn't I? One Tuesday? Yeah. So that was the day, I might have said that, she was sick. Basically she stayed in bed, she fed our son, and then I had all of the other duties to take care of. Duties in all of the sense of the word. So she could get better. She apparently had sort of this stomach bug that was going around, but not as bad as most people described getting it. which suggests that she had a bit of immunity against it. She just took a little time to completely fight it off. So, but our son never got any kind of sick, even though, of course, he was around her, most of the time. So she probably conveyed some of the immunity she had to him in utero, but any additional immunity she might have developed during that exposure, she could pass on through the IgAs. The next most common type is the IgM at about 6%. This is normally found as a pentamer, which means 5 units that are all linked together. And so an IgM antibody has 10 antigen binding sites. IgMs are great for the agglutination reaction that I described last time, so that cellular pathogens all get kind of clumped together. When you're testing blood typing, you're actually testing it using IgMs for the A antigen or the B antigen or whatever, because it makes for a very robust clumping of those cells. We're going to talk about IgMs in a little bit in a second, because they're also part of a kind of non-specific antibody response that we'll get to in a second. And then the last two over here are the least common, IgDs at 1% and IgEs at 0.02 of a percent. IgDs are B cell receptors. So the antibodies that we saw on the surface of the B cell, the naive B cell, got activated. And then on the surface of memory B cells are essentially these. So something about the heavy chains here at the end make it possible to insert into the cell membrane and act as a receptor on a B cell. The IgEs are similar. They're also antibody receptors on the surface of cells, just not on B cells that are making them, but rather they're secreted by plasma cells or whatever, and they work their way into the membrane of mast cells and basophils. Mast cells are the cells that release histamine that causes the inflammatory response. And so IgEs on the surface of a mast cell, when it binds to an antigen, will immediately cause inflammation, which is the basis of a lot of allergies. That you can have antibodies against grass pollen or pet dander or whatever it might be. If that's on the surface of the mast cell, it'll cause an allergic reaction to that thing that's not actually a pathogen. And then basophils are the least common type of white blood cell. What they do isn't very well described. What it says at the bottom down here for these antibodies associated with allergy, which I just explained is the mast cell thing, and then anti-parasitic activity. That's apparently what basophils are for. Other books that I've used that have described the same thing will go so far as to not just say anti-parasitic, but specifically about parasitic worms. Somehow, basophils seem to be associated with dealing with parasitic worms. Basophils also release histamine, but mast cells are the really big producers of that. But the interesting thing about IgE is that it seems to be a place where we see another connection between allergies and parasitic worms, which echoes what we heard in the podcast weeks ago now, it seems. So it suggests that there is a little bit more to that than just the stuff that the podcast was talking about. Yeah.
Are the antibodies of IgM composed of IgG or?
Well, all of these are different types of antibodies based on what the heavy chain looks like. And so the IgGs stay as monomers because they can't connect to other antibodies. IgMs are IgMs because they can connect to each other and they make these pentamers. So what's out on the antigen binding side of these is the same for all the different types that are made by one particular lymphocyte. But what's different is this end of the molecule. so that IgMs can form a pentamer, IgGs stay as monomers, IgAs become dimers because of how they link together at the end of the heavy chain there. So, and the heavy chains are designated by those Greek letters, mu, which is M, gamma, which is G. I should read off here. A is alpha, E is epsilon or eta, I can't remember what it is. And then the last one there, D for delta. It's just the designation for the heavy chain version that makes that type of antibody. So I just wanted to show you that from the book rather than this, because this doesn't say anything terribly different. I just like the table from the book that gives you the percentage that each is laid out and the nice table for explaining what each one does. Now, I said a little bit ago that I'm going to talk a little bit about something that IgM has to do, which is a non-specific immune response. These two graphs show us a primary response, which is what happens when you're first exposed to a disease-causing agent that you've never encountered before. And then the secondary response would be the response to the same disease-causing agent the second time, or really any subsequent time after that. The secondary response isn't a single episode, it's every episode that occurs after that first primary response. The blue curve that we see here is labeled IgM because plasma cells, when there's any kind of sign of infection, the beginning of the inflammatory response like that, any active plasma cells in your system will just start churning out IgMs for whatever they're responsible for making, hoping, so to speak, that they have the antibody to help fight off whatever is causing the infection. The red line is an IgG concentration curve. And this is looking at the specific IgG that's activated by that particular disease-causing agent. The curve doesn't start until, according to this, maybe 5 days out or so. And it builds up to its maximal concentration at about 2 weeks, according to this graph. And then it tapers off. But it never quite gets all the way back down to zero. Once you've been exposed to something for the first time, the B cells are activated, the T cells are activated, all that stuff takes place. And part of the activation process is the production of memory cells that are ready for a future exposure. The time it takes to get from the initial exposure to this disease-causing agent to the beginning of the IgG curve suggests the time frame that activation takes place. The B cell has to run into that particular antigen that it's prepared for. The helper T cell has to also. Remember, B cells don't get activated until the helper T cell releases the interleukin 2. So it takes a little while for your system to even get to the point where it's ready to start churning out those IgGs against the specific pathogen. And then within a couple of weeks, you should have fought off whatever that is. Now, the time course here might vary depending on what the exact disease-causing agent is, but this is sort of a general curve. And that 2 weeks here might be more than just when you're sick. You don't have an illness for 2 weeks all the time. There's going to be an incubation period when you're exposed to a disease-causing agent before it causes any symptoms in your body. So that's, you can kind of think that works in with this. But as you build up that immunity to it and those IgGs are available, then your immune system can start fighting off that particular disease as it's occurring. After you've been exposed to something once, the secondary response is what happens in your body every time after that, because you're now immune to whatever that was. So if you're exposed again, there's the same blue curve for IgM, The curve looks a little bit different. I think that's just that it wasn't drawn exactly identical. But this is a non-specific response. It's not because this is the second time you've been exposed to something. It's the exact same response as the first one. So those two curves really should look the same. What's different is the red curve. Now that you have immunity to whatever this disease-causing agent is, the second time you're exposed to it, you'll see a very rapid increase in IgG numbers. And again, this is specific to this particular disease-causing agent. The point at which it makes the same amount of IgG as the primary response here is probably 4 or 5 days into the response. And it's already making as much as it needed 2 weeks to get around to doing before. And if this disease-causing agent has an incubation period of 4 or 5 days before you start showing symptoms, you've already worked up enough antibodies to fight it off like you did the first time. But you keep making antibodies, and the peak of the IgG curve, it's way up here. Granted, it's a couple weeks out, but it's a lot more. Now, one thing that this graph doesn't show, and books that have been showing some version of this graph for a few years have left out what I think is a very important aspect of it, is the scale on the y-axis. Now, the scale on the x-axis is time, and it's a linear scale. The distance from 0 to 1, 1 to 2, 2 to 3, they're all equivalent, and that's 1 week, that's another week, that's another week, that's another week. On the y-axis, it's not represented here, but it is true, this is a logarithmic scale, which means that it's an exponential scale. I'm going to draw it in on the secondary response just because that side's got some stuff written on it. But if we put tick marks here that are spaced equally apart, each tick mark is a factor of 10 difference. So this first one might be 0.1 whatever units of antibody in the serum. The next one's going to be 1, the next one's going to be 10, and 100, and 1,000, and 10,000, and 100,000, like that. The peak of the first primary response curve is about here, which from 1 to 10, the tick marks in between there, that's going to be about 2 or 3 units of antibodies in the serum. And then the peak here is going to be, as I've drawn the scale, above 100,000. So there's a huge increase in the amount of antibodies because it's an exponential curve. To draw this as a linear Y scale on the graph, it'd have to be really, really tall. Okay, so to compress the data to show that there's this exponential increase in antibody production, it's a logarithmic scale, which hides the fact, since it's not labeled as such, that the difference between the primary response and the secondary response is orders of magnitude in difference. Okay, that's like if you called a couple of friends, said, "Hey, come over, let's have just a little impromptu party," and you're expecting 2 or 3 people to come over, and they told 2 friends, and they told 2 friends, and somebody put it on Twitter, somebody put it on Facebook, and 100,000 people showed up. Okay, that's the kind of change in number we're talking about. So it's impressive enough that the red curves are of different heights, but really the numbers behind this data show that there's a huge increase in the secondary response, which always gets left out in the books that are showing this. Speaking of the books that are showing this, oops, that's not where I wanted. This is the graph that our book shows, and again, they don't have any scale on either the X or Y axis. I kind of like the fact that they don't have a scale on the X axis because the couple of weeks that we saw in the previous one, I think, can vary a little bit under different conditions. I kind of wish that this wasn't one continuous thing because the secondary exposure might be years and years in the future from the primary exposure. But no actual time scale there. Doesn't really matter. But on the y-axis, they definitely don't show the logarithmic scale there. But still, the difference between this peak here and this peak here is exponentially greater, probably 4 or 5 times as many antibodies. So if the peak of the first curve is 1, the peak of the second curve is going to be 1,000, 10,000, something like that. So, sure.
Primary response, is that active?
Right. So, well, not necessarily. And I'm going to get to that question in a sec. So this picture here kind of shows what's happening in terms of the cells. Let me make this picture bigger, and it'll be better without the lights. So this is showing over here on the far side 3 cells, and what they've done is they've depicted the antibodies by color as these are 3 separate naive lymphocytes, and they each make their own unique antibody. And the red colored antibody is the one that can recognize this triangular shaped antigen. Okay. So it binds to the red one. It doesn't bind to the blue one. It doesn't bind to the purple one. When it binds to the red one, that causes this B cell to be activated. For the sake of this picture, they just jumped from binding to its antibody to activating and proliferating. But between those 2 steps, we already saw it gets sensitized, the helper T cell has to come into play, all that stuff. But this one cell then divides into clones of itself so that all of them make the red colored antibody, which is the one against this antigen. Most of those cells, as they divide, will become plasma cells, which secrete the red antibody to help fight off whatever this antigen is. But then it also gives rise to a memory B cell. And then for the secondary response, no activation is required. We have a cell that's already activated. It's the memory B cell. It gets exposed to the same antigen again sometime in the future, and it just goes ahead and makes copies of itself. Some memory cells and plasma cells. And all of these cells, which can be activated or can be produced right away when the antigen shows up, are going to start churning out those antibodies, and you see that secondary response go way up. But all of these are churning out the red antibody. All of these cells, which are just clones of this original cell, make the exact same antibody in terms of what antigen it recognizes. It's not they're not making purple or blue antibodies here. It just one cell becomes very active. During the primary response, it becomes very active to fight off that infection, which can take a little while, maybe a couple of weeks to fight off. And then the second time and every subsequent time after that you're exposed to the same thing, that memory B cell just makes a whole bunch of copies of itself that are ready to fight off that infection. Don't need helper T cells to do this. They're ready to go right when they're exposed to the antigen. So imagine that the antigen that's depicted here is the chickenpox virus. Okay. So hopefully when you're a kid, you're exposed to chickenpox. And I say hopefully when you're a kid because if you're exposed to chickenpox when you're an adult, it's a really horrible experience. Kids can handle chickenpox a little bit easier. And so the chickenpox virus binds to this cell here. Chickenpox virus is phagocytosed by other cells that are then presenting that to the CD4 cells that get activated to be helper T cells. Those activated helper T cells and the sensitized B cell interact, which allows for the B cell to become activated and start to proliferate and differentiate. And then you have all these cells that are churning out antibodies that help to mark the chickenpox virus so that you get rid of it in your body. But you also have memory B cells that were not part of fighting off the chickenpox virus the first time you're exposed to it, but they are the immunological memory of that. So if you're exposed to it again, you have memory B cells that can go ahead and fight off that infection, and it's going to be such a strong response and so quick that you'll never get around to experiencing the symptoms of chickenpox, and you're immune to chickenpox. You don't get it again. Some people can get chickenpox twice, but that happens because the initial exposure is weak and they don't work up a full immunity to it. And so the second time they get chickenpox, it's still the primary response. And they finally build up an immunity to it, and any subsequent response after that will be a secondary response. So back to your question, Ali, about whether it's
Primary.
But
Is it primary?
yeah, you're asking as a primary response.
Yeah.
Active.
Yeah.
Okay, so active and passive in terms of the adaptive immune system is whether you're making it or something else is making it. So passive immunity is like what a newborn gets from its mother, because the mother's making the antibodies. In terms of who's making the antibodies, it's you, so that's active immunity. The consideration to make, however, I think is it naturally acquired or artificially induced, which are the terms that I used originally. I don't like those terms, but which is to say, what I just described is if you're a child, you get the chickenpox, you develop an immunity to it. Just as likely, and hopefully more likely these days, instead of getting the chickenpox, somebody's vaccinated against the chickenpox. And so they're exposed to a non-virulent form of the chickenpox virus, but that's still going to cause activation of this B cell, and you develop memory B cells against it. And then if you're ever actually exposed to chickenpox, you'll have the memory cells available already, and you can respond to it and never actually get chickenpox. It could be influenza. We could give the same story for the flu shot. You get the flu shot. That causes the activation of B cells, and you have memory B cells against the strain of the flu that the flu shot's for. And then if you're exposed to it during flu season, provided that everything went correctly and the flu shot's effective that year, then you have memory B cells against that flu, and if you get exposed to it, you fight off the flu and you don't get sick. So, or you could say it for any vaccines. Okay. Vaccinations basically stimulate the primary response with a non-virulent form of the pathogen so that you develop the immunological memory against it. And then the secondary response is what you see when you finally do get introduced to that thing that you're already immune to, thanks to the vaccine. So, I'll check this in the book. So these two parts of the curve could easily be not just primary response and secondary response, but vaccination and immunity. And we don't label them vaccination and immunity, but vaccination stimulates the primary response so that you're immune to something, and every subsequent exposure to it is going to be a secondary response. Okay, so I wanted to just go in there and finish up the immune system. I thought it would only be 10 or so minutes, but more like a half hour. So, but you know, I can talk. So let's get into the, I don't want to close that. The respiratory system. Now in lab, we already touched on the respiratory system somewhat. So we're going to go pretty much right to the functions of the system. So the first part of this chapter is just talking about the organs and structures of the system. We did that in lab. The book talks about the conducting zone, which I broke up into the upper respiratory tract and lower respiratory tract. And the division there is basically the upper respiratory tract is everything in the head and neck. It stays open because of bony structures like the skull and the vertebral column that keeps the pharynx open. But then the lower respiratory tract is everything that stays open because of cartilage. And so that's the the larynx and trachea and bronchi, down to the bronchioles and all that deep in the lungs. And then the book goes on to, it broke the system down into conducting zone and respiratory zone, which is fine. In lab, we just concentrate on the conducting zone, the structures that we can see. The respiratory zone is when we get to the end of the respiratory tract. There are air sacs, the alveoli, that are coming off of respiratory bronchioles and alveolar ducts. And they're surrounded by capillaries, and gas exchange takes place between the air in the alveoli and the blood in the capillaries. The blue capillaries and vessels that we see there are coming from the pulmonary artery side of things, and then the red, which is carrying the recently oxygenated blood, leaves through the pulmonary veins side of the system. So what we want to talk about today is really about the functions of the respiratory system. And there are basically 5. One is ventilation, which is breathing, which we also talked about a little bit in lab, but I'm going to talk about more here today. And then we have external respiration, which is air to blood, gas exchange. And then there's transport of gases, which is through the blood. And then we have internal respiration, which is blood to tissue gas exchange. And then the last, or the end of respiratory function, is in cellular respiration, which is in cells. How those gases are used and modified in cells. So we'll talk a little bit about some of the function behind breathing. We talked about it in lab a little bit. The muscles that expand the rib cage and therefore enlarge the lungs. And then we'll look at how gases are exchanged. We'll probably get to this stuff next time, I would imagine. We're actually going to look at external and internal respiration together because they're kind of 2 sides of the same coin, even though they're on either side of transport of gases. And that's just because I've given you this list kind of in an anatomical order. So external respiration takes place in the lungs, and internal respiration takes place at your tissues. And so between there, the blood has to transport the gases from the lungs to the tissues. But we'll actually look at that separately. And then cellular respiration is considering the chemistry behind using oxygen and producing carbon dioxide. We'll sort of close out with that, which is good because it's a good picture of how this chapter and the next 2 chapters that we're dealing with are tied together. In the book, and let me just, in the book, now that we're starting the respiratory system, we're in Unit 5, which is environmental exchange. It's a little bit more of the title, but environmental exchange. The respiratory system, we exchange gases with our environment. Then we're going to look at the digestive system where we get food from our environment take the nutrients out of it, and then return the waste products. And then the urinary system is dealing with some of the other waste products that we get thanks to ingesting things through the digestive system. So those three chapters, those three systems are tied together: respiratory, digestive, and urinary systems. And one of the ways to illustrate how they're tied together is going to come from talking about the cellular respiration thing at the end of this step, which again, we'll get to next time. But so what I want to get to today, and I may get around to starting the external respiration stuff today, but not in this thing, is about breathing. So in lab, I talked a little bit about muscles expand the rib cage, the diaphragm goes down, the external intercostals help to sort of pull the rib cage up. And I showed you that model with the plastic bell jar and the two rubber balloons inside, and how just moving the thing that's supposed to be the diaphragm at the bottom would make those balloons enlarge as it helps to pull air in. I want to talk about the point of that and what's behind it in terms of the mechanism of breathing. So you probably can't quite see it here. At the top of the screen as I have it now is a little equation that says P1 times V1 equals P2 times V2. What this means is that there's a very close relationship between pressure and volume. When you measure pressure and volume in a system at one point, pressure and volume in that system at any other point has to equal that relationship. Essentially, pressure and volume are inversely related. Okay. So this picture depicts it. Let's say these two beakers here are liter-sized beakers when we put the lid on it. So we have a mixture of gases, air, in this beaker. It's a liter. If we push the lid down so that it becomes a half a liter of gas, we haven't let any of the gases escape. It's still in that beaker, just taking up half the volume. What we're talking about here is if we're just capturing air from here in the room, for instance, the pressure at time point 1 is going to be 1 atmosphere of pressure, and the volume is 1 liter of air. Okay, what's 1 times 1? Yeah, don't you hate when you have to do math in your science class? Yeah. So the pressure times volume product has to be equal at the second time point. So the second volume is half a liter. What does P2 have to be for this equation to be equal? 2. Yeah, 2 atmospheres. So if we decrease the volume of this air by half, we are basically increasing the pressure inversely, meaning multiplying it by 2. 1 times 1 and 2 times a half equal the same thing. If we push this lid down so that the volume of air in the beaker was 1/4 of a liter, what would the pressure be? Yeah, 4 atmospheres. And we just need the pressure volume to be equal. This is essentially what Boyle's law says, that pressure and volume are inversely related. If volume decreases, pressure increases. As volume increases, pressure decreases. You're not going to need to worry about calculating any of this stuff. Granted, the calculations I just showed you are very simple, but the amount of change that takes place in the system is so small, we're not really going to worry about the exact numbers for volume, at least. We'll just know that the pressure is changing because of the volume changing. Now, when we use pressure, we're actually not going to use atmospheres because that's actually a pretty big unit. The pressure of air at sea level is 1 atmosphere. We can also measure that in millimeters of mercury, which is a unit we're used to using for blood pressure. There's 760 millimeters of mercury worth of pressure in 1 atmosphere. Okay. So we could just as easily say 1 liter of air at 760 millimeters of mercury, decrease that to half a liter, you're going to double 760, what would that be, 15, 20 millimeters of mercury worth of pressure. Okay. The pressure changes we're talking about for breathing are nowhere near that big. When you take a breath in, the pressure in your lungs has dropped by a couple of millimeters of mercury. And when you exhale, it's because the pressure in your lungs has risen by a few millimeters of mercury. The volume changes in that are pretty small. If we work on the assumption that the lung capacity is 6 liters, as we used with the lab material, the amount of volume change necessary to decrease pressure by 2 millimeters of mercury is very small. It'd probably be going from 6 liters to like 6.02 liters. I don't know the exact number, I've never done the math, because it's not necessary for this class. But very small changes in volume will cause very small changes in pressure, and it's enough for breathing to take place. Now, the pleura, the serous membrane that surrounds the lungs and lines the inside of the cavity, is a closed system. And part of the mechanics of breathing depends on that. When the diaphragm goes down, it pulls the parietal pleura down, which is going to pull the visceral pleura along with it because you can't increase the, well, if you increase the volume there, the pressure goes down, but it's just going to pull the lungs along with it. So the lungs will expand right along with the rib cage. So here's just a picture depicting the diaphragm contracting and going down. That's going to pull air in. What happens when you're breathing is you expand your rib cage, your thoracic cavity a little bit, so that the volume of the lungs goes up and the pressure in the lungs goes down. It only has to go down to about like 758 millimeters of mercury. And that's enough for air to move from 760 millimeters of mercury outside your body, in your body, until it's equal between the two places. So now your expanded lungs have filled with air that's 760 millimeters of mercury in pressure. These muscles relax, the diaphragm and the external intercostals, which is a little hard to read, but that's what this part of the picture. So that's what expanded the rib cage. They relax. Elastic tissue in your lungs that was stretched out when your lungs expanded pulls everything back down, and the diaphragm goes back up, and the rib cage sort of settles back down into place. And now the lungs are smaller in volume, and the pressure goes up by just a little bit. It was 760 at the end of that inhalation. All of that air that got into lungs is now at a pressure of maybe 762 millimeters of mercury. Very small pressure change, but enough to push the air out. And we exhale. That's basic breathing. And it's just changing the volume of the lungs changes the pressure so that air rushes in down a pressure gradient when your lungs expand, and air rushes out of your lungs because of a pressure gradient when your lungs recoil. Okay. And that's just basic driving mechanics of ventilation. We looked at this graph, this graph in lab. We did the spirometry thing in lab. This picture depicts the parts of the nervous system that are responsible for controlling breathing. There's a couple of nuclei in the medulla and a couple of nuclei in the pons that are important for controlling breathing. The most important one, I would say, is the dorsal respiratory group, DRG. The cells in the dorsal respiratory group are autorhythmic. That's a term that we learned when we were talking about the heart, the SA node or the AV node or whatever. Those cells in the heart were autorhythmic. They generated action potentials automatically. These neurons do that also. That's a little unique for neurons. This is a rare region of the nervous system that can do this. But the neurons here, they generate an action potential. They never get to a resting potential. They just slowly depolarize again until they hit threshold. So signals are sent down the axons leaving the dorsal respiratory group, which will eventually innervate the diaphragm and external intercostals, causing those muscles to contract. The dorsal respiratory group firing rate is what establishes your respiratory rate. Resting respiratory rate is usually thought of as being, well, the range is usually 12 to 18 breaths per minute, but 12 breaths per minute would be 1 breath every 5 seconds. So action potentials are generated in the DRG every 5 seconds, which go down and cause those muscles to contract. And the muscles relax. And then another action potential 5 minutes later causes muscles to contract, and then they relax. Usually you breathe in for about 2 seconds, you breathe out for about 3 seconds in that 5-second time frame. The dorsal respiratory group can also activate the ventral respiratory group when needed. The cells here are not autorhythmic. They have to get input from the dorsal respiratory group. And that will happen when additional muscles are needed for deeper breathing, whether it's the sternocleidomastoid, scalenes, pectoralis minor, or those that is listed increase the volume of your lungs when you breathe in, taking a really deep breath, or it can activate the abdominals and internal intercostals, which will increase, I should say that differently, which will cause the lungs to lose volume faster, pushing air out. So they're just showing you some of the muscles here, the internal intercostals, and they're suggesting the abdominals here. Well, no, I should say that they sort of hidden the abdominals here, but the abdominals would be affected. What they're highlighting here, the pectoralis, these are serratus muscles, I think they're called. These are muscles of inspiration, exhalation. So when you need to do more to breathe in or out, the ventral respiratory group will activate the other muscles. The dorsal respiratory group is just controlling the diaphragm and external intercostals for basic breathing. Now, the reason why the DRG would need the VRG to do a little bit extra work is if a signal comes down from the apneustic center or the pneumotaxic center, the two pontine, meaning in the pons nuclei, that influence DRG. The apneustic center will increase activity in the DRG so that it will breathe faster, and the pneumotaxic will slow it down so that we breathe slower. Now, the question here is what tells these two centers to do their job. And in this picture, they don't really say, they don't show anything, but higher centers, like your cerebral cortex or your hypothalamus, those sorts of things higher up in your brain, can send signals down. If you're going to talk, your cerebral cortex, which is controlling speech, it's going to tell you to breathe in the correct pattern to produce that speech. Or your hypothalamus, which is tied into the autonomic system and homeostasis in general, can tell your breathing to change, like if you're in the middle of a fight or flight response. Fight or flight, sympathetic system, would control smooth muscles or cardiac muscles. These are skeletal muscles. The autonomic system does not control skeletal muscles. So changes in breathing that go along with the fight or flight response are because the hypothalamus, which is right here, tells the pontine nuclei that you need to breathe deeper. to get more oxygen in while you're running away from a threat or something like that. Also, another input that can come into the pons or the medulla directly can be peripheral sensors. If your blood chemistry changes, then your breathing is going to change with that. So that'll go into, that's more input that can influence these areas here. In this part of the chapter, they go on to talk about a few things that control this. They mention central chemoreceptors and peripheral chemoreceptors. Chemoreceptors are just going to be cells that are sensitive to chemical stimuli. Central chemoreceptors are ones that are in the central nervous system. Peripheral ones are outside in the periphery. Central chemoreceptors are going to be linked directly to the hypothalamus and can cause descending input to these structures. Peripheral chemoreceptors are going to be out in the bloodstream. Usually the main ones are in the wall of the carotid artery and the aorta. And as your blood chemistry changes, if your blood becomes too acidic, pH drops, something like that, that can influence breathing. Now, to understand the relationship between things like blood chemistry or pH and controlling ventilation, we also have to kind of think about gas exchange. And I'm not going to get through all of gas exchange today. So we'll come back to the idea of how pH influences breathing later on next time. But I want to start talking about gas exchange by introducing a couple of more gas laws. So what I wrote up here, this is about Boyle's law, which is the relationship of pressure and volume, which is behind the mechanics of breathing. The next one I want to talk about is Dalton's law, which can be summed up with the equation P subscript T, which means total pressure of a mixture of gases, is based on the pressure of one gas plus the pressure of a second gas plus the pressure of a third gas plus the pressure of a fourth gas, et cetera, et cetera. The subscript T next to P means total pressure. But all of these others, when we see P for pressure with a subscript depicting a particular thing, that's what we call the partial pressure. So what Dalton's law basically says is the total pressure of a mixture of gases is the sum of the partial pressures of those individual components. So the total pressure of the air we breathe is the partial pressure of nitrogen gas plus the partial pressure of oxygen gas plus the partial pressure of water vapor, H2O, plus the partial pressure of carbon dioxide, plus the partial pressure of a few other things. So the table that's on the screen right here is a list of those partial pressures. So the partial pressure of nitrogen, partial pressure of oxygen, water vapor, carbon dioxide, and the other things, all of those add up to 760 millimeters of mercury, total pressure of air at sea level. We don't actually measure the partial pressure of the individual gases. The picture down here kind of suggests that idea. Here we have a beaker with oxygen gas in it at 159 millimeters of mercury. Here we have a beaker of nitrogen at 598 maybe millimeters of mercury. You put those two together in a container and you're going to get a total pressure for them, which is those two numbers added together. Really, what we do is we look at the whole composition of gases. We can take a sample of air that we would breathe and separate that on a spectrophotometer, which will tell us exactly how much of each type of gas is in that air sample that we're looking at. So over here, the percent total composition is what we would get from that. We'd be able to establish that the air we breathe is 78.6% nitrogen, 20.9% oxygen, 0.04% water vapor, 0.004% carbon dioxide, and 0.0006% other stuff, like carbon monoxide and argon, which adds up to 100%. So we know what the partial pressures are of things because 78.6% of 760 is 597.4, or 20.9% of this is, so we can just do the math. We know what the composition of the air we breathe is, and we know what its total pressure is, so we can just sort of back calculate it. Okay. But what Dalton's law is saying is that a mixture of gases is the summation of all the partial pressures. Okay. Why that's important to us is based on another thing that's not really a law so much as an important concept, but it's often called the ideal gas law, which is the individual components in a mixture of gases, like the air around us, the molecules of oxygen, the molecules of nitrogen, those sorts of things are so far apart from each other. The density of those substances is so low, they don't ever run into each other. So we can treat the component gases in the air we breathe separately, which is important because when we breathe, we're pulling in oxygen and we're exhaling carbon dioxide primarily. There's a mixture of gases, but the percentage of what we're inhaling and the percentages of what we're exhaling are different depending on the specific gases involved. Because the partial pressure of oxygen in the air we inhale is higher than the partial pressure of oxygen in our blood. And so oxygen preferentially moves into our blood. The partial pressure of carbon dioxide in our blood is higher than the partial pressure of carbon dioxide in the air that we breathe. So it preferentially moves out of the blood. Those two are acting independently. The partial pressure of oxygen moves oxygen into our blood. The partial pressure of carbon dioxide moves carbon dioxide out of our blood. So what Dalton's law is saying technically is a mixture of gases is the total pressure of a mixture of gases is the summation of all of its partial pressures. But why that's important for us is because that defines what partial pressures are, and those partial pressures change whether we're looking at the air outside of our body, the air in our lungs, and it defines how gases move with our blood. Which brings us to how gases dissolve. So the solubility of gases in liquid brings us to the third law that's talked about here, which is Henry's law. And I don't have anything to write up here on the board to go with Henry's law. All Henry's law tells us is the concentration of a gas in solution is equivalent to its partial pressure. To explain this, I like to use the idea of carbonated beverage. At the Coca-Cola bottling plant, wherever that happens to be around here, maybe in Enfield or something like that, they take a syrupy concoction that is uncarbonated Coke and put it in a bottle, and then they inject a mixture of gases that's rich in carbon dioxide to carbonate the gas. Sorry, carbonate the soda. And then they cap the bottle. So inside the bottle, the air that they've injected has a high percentage of carbon dioxide, much higher than the air around us. And what Henry's law basically tells us is that high partial pressure of carbon dioxide in the air that's put into the bottle will cause carbon dioxide to dissolve into the Coke. And at that point, we consider it carbonated. But really, when we think of carbonated soda, we think of all the bubbles. You don't see the bubbles until you open that bottle. Because what happens is when you open the bottle, inside there's a lot of carbon dioxide, outside there's very little. So maybe, here's our bottle of Coke. The partial pressure of carbon dioxide inside, I'm making this number up. Let's say that it's 2.5 millimeters of mercury. And then outside, what was that number here? In the air we breathe, the partial pressure of carbon dioxide is 0.3 millimeters of mercury. So when you open up that bottle of Coke, carbon dioxide will rush out of the bottle. Now, the air at the top of the bottle had a high partial pressure of carbon dioxide in it. And the carbon dioxide that was dissolved into the water was based on that partial pressure. Now that we've uncapped the bottle, carbon dioxide leaves, and it's going to come out of the water solution that's the Coke, and that's the bubbles that you see coming out. Okay, because it's coming out so fast, that difference there is a pretty sizable one. That the carbon dioxide will come together in little air bubbles of that carbon dioxide gas, and you see that coming out. Now, how that really works perfectly, and this is not terribly important to the respiratory system, but the edge of the bottle is not perfectly smooth, and so carbon dioxide molecules will all kind of stick to particular places on the bottle, and enough of them come together, they form a bubble, and that comes out. And that's the carbonation you see in the thing. That's essentially based on what Henry's law is getting at, which is essentially just that gases dissolve in water. Okay. What it means for us is when we talk about gases that are dissolved in water, we're going to continue talking about their partial pressure, although they're in a liquid rather than a gas solution or mixture, because the solubility of gases is proportional to their partial pressure, or dependent on their partial pressure. So when we're talking about oxygen moving into the blood or carbon dioxide moving out of the blood, that's going to be driven largely by the partial pressures, how we're going to consider it. So I wanted to define those laws before we get into the gas exchange and the gas transport stuff, which will help describe that stuff. So I could start talking about that now, but I need definitely more than 5 minutes. So we'll stop there today. Next time we'll come back to the gas exchange and gas transport is part of the chapters.
On Monday.
Sorry?
On Monday.
Oh, good point. Yes. A Massachusetts holiday, Patriots Day, is the 18th of April. School is closed on Monday. We are not going to have any kind of makeup for that. Like after President's Day, Tuesday followed a weird schedule. Following Patriots Day, they don't do that. So next week, no Monday lab because there's a holiday. Monday lab will just do their thing the following week, which means that Monday will be a week behind the Wednesday lab for the remainder of the semester, which is okay because the last week of classes is just Monday and Tuesday. So the Wednesday lab will end a week before the Monday lab anyways. So it'll all work out just fine. You can wait till I finish talking before you start running that. Otherwise, have a good day.